Hello everybody. In this video we will talk about reaction of ether with an acid like HI or HBr. So this is a little bit harder example than what we did in our last video. Okay, so in our previous video. So let's try to name this one. So this one would be your ethyl, and this is a benzene ring. So this one called as phenyl. So it's ethyl phenyl ether, or you can call it ethoxybenzene. Okay, so that's you can name this way. Okay, so what would happen if we react with an excess of HI? So let's try to go forward just like we did in the last one. So it's critical you all try to draw the mechanism, because this is the best way to learn organic chemistry. And if you want to learn a little bit more about it, then you can see where you are doing your mistakes. So obviously the step number one is you abstract the proton and the electron will go away towards the I. So I will write it out. So if you know, benzene ring is like, if I have to draw it out, all the double bonds, it could be either this or it could be, so the double bonds are delocalized, right? So you can have double bonds. So the basic idea is all of the carbon atom here has double bonds. So everybody has one double bond. So when you have one double bond, these are sp2 hybridized carbon atoms. Okay, so sp2 hybridized carbon atoms. So all these carbon atoms are sp2 hybridized carbon atom. Now this gonna play an important role. So I'm gonna move these here, and I will resize this, and we will keep this in our notes. Okay, so this is our sp2. Now why that is important? Well, let's see. So why those are important? So we got our benzene ring, and then we got our O, CH2, CH3, and one of the oxygen has abstracted a proton. So we got our H, and then there is positive charge right there. So oxygen has 3 bonds, so it should have positive charge. And how can we, what should we do next? Every time you have a positive charge on oxygens, you try to neutralize it. Well, I can neutralize it by getting rid of my proton. So which means that's basically going backward, but we want to move forward. Okay, so this is where the fun begins. Okay, so now the question is, how would you neutralize it? So a couple of ways you can neutralize it. My I minus could attack on this particular carbon atom right there and move these 2 electrons here towards oxygens. Okay, so I will do that. So the product I will be making from here is gonna be this OH. And on the other side, we got our CH2, CH3, and your I. Okay, so this is the attack of I minus on the CH2 is an SN2 attack. So this is an SN2 attack. Okay, so this is an SN2 attack, but this SN2 attack is not gonna be possible on this particular carbon atom. So you cannot attack here. So this attack will not be possible. So this won't be possible. So here is why. So remember what kind of hybridations we have on this carbon atom. So if you look at here, all of these carbon atom are sp2 hybridized. And sp2 hybridized, if a carbon atom is sp2 hybridized, then SN2 attack is not possible. So SN2 attack does not happen on an sp2 hybridized carbon atoms, right? So you cannot do this. So I'm gonna do this right down here. So you So you got positive charge. So you cannot do this. So this I minus will not, so this won't happen. I'm just showing you what would happen if that thing happens. Okay. So basically, you're going to get I here. And on the other side, you'll get CH2, CH3. Okay, I will make this slightly to the left. And we got O and H. So this product will not happen. So this product will not gonna happen. And why will not happen? And why this won't happen? Because we cannot do an SN2 attack on a sp2 hybridized carbon atom, which is here. Okay, so this reactions, unlike our previous example, so this reactions will stop here. This is your final product. So this is going to be your final product. So even if you have excess HI, you cannot replace the OH with an I minus. So that reactions won't happen. So this is slightly different than previously. So you see all the reaction that we have been doing is an SN2 attack. However, if you have tertiary, if you have a possibility of making either tertiary benzyl or allyl carbocation, then the reaction will follow with SN1 mechanism. But you still gonna make, if you have excess HI, you still will be making your iodines is gonna be replacing on either side. So like if you have something like this, so in this case, you would have, so you have HI excess. So now you got OH plus, and then because the leaving group here is going to give you a tertiary carbocation, so you will get your tertiary carbocation here, and your other side you will get I. Now this I is your one product, and here, oh, not I, other side you will get OH. Now this portions would react with excess HI to give you OH, H plus, and then I minus would be replacing this one. So you got your water plus I. So that's basically CH3I. And on this side here, you have your I minus also. So the I minus will do an SN1 reactions right here. So it will go towards the carbocation, and then you can end up making this. So you have two products, right? So here and here. So either of those scenario, so how the reaction is proceeding, that's what matters. So this case, you had an opportunity of making a tertiary carbocation, so the reactions follow SN1 route. So that's the only thing I want to mention here. So let's go back. We will, previous example. So when you have on either side primary carbocation, not carbocation, primary carbon atom, you replace iodine, and the reactions follows with an SN2 attack. But the moment you got an opportunity to make a tertiary carbocation, you're still gonna get iodine here, but the reaction just follow with SN1 route. All right. And if you have a sp2 hybridized carbon atom on one side, then you're not gonna be able to replace the OH with an I. There are other methods to do it, but by this method, we cannot do it. Okay, let's stop here.